Okay, recording has been started. Hi, everyone. I would like to step in for a minute before passing the ball to our co-director of the FoRCE, Merve Doğan. So all recorded FoRCE seminars currently available at two websites. One of them, IEEE Control System Society. Here is the link, IEEE-CSS.org webinar with videos and webinars. You need to scroll down. There are body lectures, preliminaries, and FoRCE webinars. When you click the FoRCE, basically you can see all the seminars. We need to update it. It is apparently my responsibility, but I will connect with IEEE to update our 2022 and 2013 seminars. If you also want to access them, it is also available on initially on my YouTube page, Yucelen. So like here, seminars on robotics and control engineering. If you click here, you can have all these presentations. So as this being said, welcome everyone. I am now stop sharing, passing ball to to Merve Doğan, and she will introduce our speaker, Kamesh Subbarao.
Thanks, Tansel, for the talking about this webpage. Yes, as you said, we are getting a lot of emails, but it is IEEE CSS webpage. Kamesh, at the same time, if you want, you can share your presentation. Well, hi everyone. Welcome to today's Forum on Robotics Control Engineering online seminar. Before we start, I will also talk about FoRCE a little bit. FoRCE is dedicated to provide free, high-quality outreach events and online seminars to reach broader robotics and control engineers. Thus, we periodically invite distinguished people like Dr. Subbarao to give their talks on recent research results on the robotics and control engineering. The aim of the FoRCE connecting academicians as well as the government industry researchers with each other through the research and education discussions. So we cordially hope that you will enjoy all the FoRCE events and you will find them highly valuable to your own research interests. And let me also mention about the rules, like we will be all muted during the talk. If you want to ask questions, please do that after the presentation. You can do that simply by unmuting yourself, or you can post your questions to the chat box. And we are recording this session and it will be posted to FoRCE webpage as well as the IEEE CSS webpage, as Tansel said. Well, jointly with Tansel Yucelen, we are very proud today to host Dr. Subbarao. Kamesh is the Jenkins Garrett Professor and Director of the Aerospace Systems Laboratory in the Mechanical and Aerospace Engineering at the department, at the University of Texas at Arlington. He received his BTech from IIT Kanpur, ME from IIS Bangalore, and PhD from the Texas A&M University. All of these degrees are in aerospace engineering. Since joining UTA, he has contributed in the areas of flight mechanics, controls, and astrodynamics, nonlinear adaptive control, linear and nonlinear filtering estimation, cooperation and coordination for the multiple unmanned vehicles subject to measurement uncertainties, and distributed time delays. Dr. Subbarao his research has been funded largely by ONR, NASA, NSF, AFRL, DARPA, and Lockheed Martin. He is a fellow of the Royal Astronautical Society and the American Astronautical Society, associate fellow of AIAA, and senior member of IEEE and ASME. He has authored over 200 journal and peer-reviewed conference publications and is the associate editor of the AIAA Journal of Guidance, Control, and Dynamics and the ASME Journal of Dynamic Systems, Measurements, and Control. Well, for all of you who are here, I would like to thank Kamesh for participating in our forum as a speaker. Kamesh, whenever you are ready, please go ahead and start.
Thank you very much, Merve and Tansel, for the invitation. And one thing, do I have about 40 minutes, 45 minutes, or the full, do I go for the full hour?
Maybe go ahead.
It's up to you, but we usually want to just spend last 5-10 minutes for questions.
Right.
But if time doesn't allow, since you already put your email there, they can email
Okay.
you, I think, with the questions.
Sure, fantastic. And I will also turn off my video. So yeah, thank you very much again for the very kind introduction. A little longer than I hope you would read, but yes. So I will talk today about stability and performance assessment of cooperating teams of multi-agent systems. I'll get to this shortly in terms of what exactly is the specific application that motivated this work. So we've been working in this particular area for about what I'm going to present is going to be work that was performed over maybe the last 3 years or so, so 2 to 3 years primarily, and yeah. So just to give you a little background of my lab here at UT Arlington, my lab primarily focuses on modeling, simulation, control, and estimation. Ours is a combined department with the mechanical and aerospace engineering students. So the application areas are sort of across spectrum. So there are mechanical systems as well as aerospace systems. And some of the application areas, like I mentioned here as a bulleted list, can range from have ranged from bipedal locomotion, which was actually a funded project from DARPA, and the more recent ones have to do with cooperative control and in uncertainty quantification and some spacecraft multi-sensor fusion applied to say proximity navigation type of scenarios. So this has been the focus of my research group for some time. And more specifically, the areas that I am actively researching today with my research group would be, like I said, on multi-sensor and data fusion for proximity navigation, GPS denied navigation, space situational awareness. These are all typically funded through small business rogue space from New Hampshire and from AFRL. Some other work is funded basically in the areas of set theoretic approaches for model predictive control using the idea of reachable sets. Again, this is more so in the hypersonic re-entry type of problems, as well as autonomous ship tech landing type of problems, funded again by ONR, and in this case, the FoRCE. So the other areas have been in, say, on the side of uncertainty quantification. Most of that research has been in the air traffic networks, UTM, advanced air mobility type of applications funded by NASA. But what I'm going to talk about today is a project that is close to finishing, and it is essentially in the area of swarms of unmanned aerial systems. Now, with the objective to try to come up with ways in which you can analyze stability and provide performance guarantees primarily for cooperative unmanned systems. The idea here is more to study the aggregated or the cooperative system rather than focus on the low-level control issues, which we assume in this case is somehow the low-level controller is already robust, has already been developed using your favorite choice of controller. I will give you what kind of a controller that we assume that keeps the low-level systems all stable and functional. But then we are looking at how these teams are connected, and when they are connected, how do they perform? And what kind of performance guarantees can one provide for these kind of cooperative systems? So just again, a brief, just a snapshot of the kind of things in the lab. We have drones, we have rovers, we do a lot of outreach, a lot of work in this particular area. So not only are we doing theory, but we're also putting them onto physical systems and testing them out in our labs. So many of the algorithms that I'm going to talk about, or the results that I'll talk about, have been actually tested on systems that are presented here in this slide. So just a quick background to what kind of to the motivation of this particular problem. So multi-agent systems is now it's like a common phrase that is typically used in the robotics controls, dynamical systems area. We have progressed to these systems just because of the plethora of applications that are available out there. This particular slide gives you a little snapshot of how a typical, say, a battle management system, a battle management scenario works out with a team of autonomous agents. It doesn't have to be this. You can take this same area and put it into some sort of disaster site monitoring using multiple assets, flying assets, as well as ground assets, and make them work together. So a few common themes that recur in these kind of situations is control laws, whether you have decentralized control laws or centralized control laws or some sort of a mix of the two. How do you prescribe mission objectives? How do you analyze collective team behavior once you put all these vehicles together to actually perform as a team on some particular mission that has been prescribed? So these being the common themes, let us see what is out there in terms of what one can quantify with regards to the performance of a group. So how do you know that a group has done well, or how do you know, can you guarantee ahead of time that a particular group will do well or guarantee some performance once you know who the constituents of the team are, and when you put them together in a particular so what we find distinguishes how an individual performs versus how a group of individuals perform is how do the individuals within the group talk to each other. So an important aspect is what kind of a communication is set up between agents or among agents when they are in a particular group, and seemingly this specification of a connection or the connection topology among the agents is a very strong driver to how a group will perform. So if you go back and look at linear systems, if you go back and look at how to analyze performance and stability typically, we know from very early days, if we are looking at single input, single output linear systems, then we can use metrics such as gain and phase margins that will give you some metric. And these metrics are still being used to analyze single input, single output systems, albeit with a lot of restrictions, but these are well understood. Similarly, if you're looking at a multi-input, multi-output situation, you can look at singular values, study sensitivity, complementary sensitivity. All these are results, very popular results from the 70s and 80s, so like happened last century. So so if you go further and look at, say, uncertainties now prescribed on a particular system. So, well, the robust aspect of it was all covered again back in the 80s and stuff through mu analysis with Doyle, Packard, Ballas, and several other people. And with all those things being done, the question then is, how do you verify that your system is indeed performing well with whatever theoretical metrics that you have proposed? Well, the way we do it is using Monte Carlo simulations, very extensive kind. And this has been the way people have worked for a long time. And even today, there are a lot of legacy systems that still work the same way. Okay, we haven't changed too much in that aspect, but then more modern tools are coming to the fore. So if you look at just a breakdown of rather just a schematic of how these things look like for a single vehicle, we have a nonlinear dynamical model. Now you have an approach, you have two different ways of going about doing control design and guaranteeing stability and performance. We all understand this. On the one side, on the right-hand side, you can see that it is a linearize and design at specific operating points on, say, some specific design points here, then do some sort of gain scheduling. And after you perform that gain scheduling, you end up getting some sort of, you guarantee stability and performance at each of these design points. and then verify through extensive simulations and Monte Carlo studies what the performance of the vehicle is going to be. On the other hand, you can go the nonlinear control approach, then provide robust stability guarantees. There are ways to do that today. And then performance guarantees. These are tedious to calculate, and they are typically optimization based. But then with the increase in the with more and more a lot of new results coming through and a lot of development in how we can do these things computationally really fast. These methods are now very popular. So these are more recent approaches, and people are using this all over the place. Sum of squares, Lyapunov certificates, barrier functions. There's a lot of work from many of the researchers who are currently in this particular presentation, in this particular seminar. For example, Doctors Yucelen and Dewan and Padi, they are all experts in these areas. So what I want to get to is this specific application. Again, I'm trying to build towards the ONR application that we are working on. So we follow a similar approach. So let us say we started with the AV8 or a Harrier-like vehicle. And for this particular vehicle, we are just looking at a simple for an application that is basically a carrier deck landing problem. And for that carrier deck landing problem, I can tell you that we designed a full gain scheduled controller, which is basically designed at several operating points. And these points are all scheduled as a function of the speed, the heading rate, and the altitude, basically, because for that particular application. And we have a full nonlinear simulation that demonstrated the effectiveness of all these things. So this could be one such thing, one such way of designing a controller and guaranteeing some performance. But this is very tedious. That's the point. Now, let us assume that somehow, whatever your favorite method was, you arrived at a low-level control, which and with guarantees on whatever performance that you can guarantee and whatever stability you can guarantee. So that is this one single vehicle. But what we want to do is we want to see how does a group of these vehicles perform when you prescribe a particular connection topology. In this case, for example, there are 1, 2, 3, 4, 5 systems, and the way the communication goes between, let us say, a pair is there is some state information or some objective, some mission information that is exchanged between these two vehicles, and they talk to each other. So one talks to two and two talks to one. For example, for the other case, you can have basically you just have a unidirectional communication in this case, where you only get information from this vehicle passed on to this one, and so on and so forth. So there are multiple ways in which you can set up this particular connection topology. So a question to ask would be, what is the best way to connect them? Well, that's a different problem altogether, not the focus of this particular work, but that does beg that question. What is the best way to connect them so that you can have them perform a particular mission really well, right? So the takeaway from here is we need a framework that will allow, say, the analysis and performance of these multiple interconnected systems given some connection topology. So the question that we want to pose is, how well will this team perform? So the proposal came out from ONR, and what they wanted is essentially a set of metrics. And these metrics should be something that you should be able to evaluate really quickly. So that kind of takes away the Monte Carlo out of that particular discussion, because while I can verify, that cannot be used as a way to produce this metric, because that is very tedious and very computationally intensive. So the question that we asked is, can we derive simpler metrics that can be then computed really quickly for this particular group? So given the kind of mission that we had in mind, what was important is to understand that for the particular missions, we required the states to converge to some infinite time. So it is not just asymptotic convergence to something or something of that kind. We want to make sure that we converge to certain desired states in finite time. So in the particular example here, it was more of a threat neutralization example. So you have an incoming threat and you have an asset that has to go and neutralize that threat. So to be able to do that, you have to perform this particular mission in a finite time. So one metric would be to look at what kind of time it takes for you to and you to guarantee the convergence in finite time to that desired state, whatever that may be. Second, we want to ask the question, we want to derive some metric which is basically dependent on this particular group connection topology. So you ask the question for to derive a metric for something called a group stability margin, and then you want to ask, okay, what connection topologies are robust to say disturbance accommodation? Is there a connection topology that is preferred to accommodate disturbance when this group is performing a particular task? So whatever that disturbance may be, it could be a sensor disturbance that is injected into a particular vehicle, or maybe some other kind. And then you also want to talk about, say, performance. However you define performance, performance would be like finite time to convergence is a performance, but for the group. And then you want to guarantee this performance despite link imperfections. And when I say link imperfections, I mean things like delays in communication, or that kind, or maybe dropouts and stuff of that kind. But we particularly focused on delays in the communication in this case. So, at the heart of everything, we want to have at least a low-level controller that guarantees some performance and stability for the single vehicle. So I had shown a big example of a gain scheduled case. So rather than doing gain scheduling, we decided to follow a linear parameter varying type of a modeling framework, and use that to guarantee the performance of, say, the low-level vehicle. And this was designed for a full order F-16-like system. However, the results that I'm going to present are all going to be for the short period dynamics as an example. Okay? So this is quite straightforward, well understood technique. There are already tools out there called LPV tools that has actually been, it's a MATLAB toolbox developed by Pete Seiler and his group, who's right now who's in Michigan. So they have a set of tools that will help you, help you design an LPV controller for a low level, for a single vehicle. And the essential idea here is basically you're trying to optimize for this particular L2 gain of the closed loop LPV system G. Okay. And what you're essentially trying to do is to try to find lambda, which is basically the design parameter, which is the design variable here, such that this particular linear inequality is held true. Okay, so the methodology, I don't want to go through the details of that thing. It is very well understood in a lot of papers out there, all through the 90s, all the way to the 2000s. So there's plenty of papers. So let us see how I apply that, or how we apply that to the simple short period dynamics for an F-16 Vista like the model. So we have parameterized coefficients as a function of altitude and Mach number, which are shown. These are the coefficients, and this is how the altitude and Mach number variations are shown for each of these parameters. And we take an envelope just to design a full envelope controller. This is going all the way from 1,000 feet to 25,000 feet altitude, and going from 0.35 Mach to 0.85 Mach. This is like high subsonic, close to transonic type of a region. That was the kind of region that we worked all these systems with. Now, you can have the scheduling parameters, of course, here are altitude and the Mach number. So you go ahead and design a controller and everything works fine. So the low-level controller is designed with this sort of a description for the short period dynamics. Now, typically, when we are trying to connect multiple systems, we model. I'm just going to show how we model the connection between multiple systems. This is done. This is very well understood. Again, people just use graphs to model interactions between multiple vehicles, and we are no stranger to it. We do the exact same thing. So think of this as a collection of 5 vehicles, and there is a connection topology set up. We are primarily looking at a weighted graph So we have weights associated with each of these edges. I think of these edge weights as essentially some sort of relative importance of a particular edge over something else coming to the same node, if they are coming to the same node. R is essentially a reference. It is a reference trajectory that is supplied to somebody in this particular node. In this case, in this particular network, in this case, the reference trajectory is provided to one, and then through the communication, it just feeds through to the rest of them. Okay, this is a simple setup, and we collect the global. So if each vehicle is modeled through this, remember, each vehicle is modeled through this, but then each controller here, UI, is essentially synthesized through this particular framework of the LPV modeling framework. And the controller is an LPV controller, which has some guaranteed stability and performance margin. Okay. Now, what we do then is we can collect all of these vehicles together into some sort of a global closed loop dynamics, and let us look at the performance. Now, this is a very straightforward problem. If you assume, and now in our case, in this situation, all of them are the same vehicles, which means it's a homogeneous network where every node is exactly the same, has the same has the same dynamics as the other. So if you take a situation where, let us say, 4 vehicles, you have a reference 0 that is connected somehow to the network of vehicles like this, you can clearly see this is a standard leader-follower structure. So you just have 0 to 1, 1 passes information to 2, to 3, and 4. The variable that is passed around here is alpha. And since all vehicles are identical, they all have been designed. If the reference signal was given to each one separately, this is exactly how they follow. However, when they're connected like this, we understand this being the classic string stable behavior, where you see that there is going to be this behavior no matter what. And this is just coming because each one is following. There is a dynamical system that is following another dynamical system, and the growth here is just because of that dynamics here. Okay, this is just without anything. There is no uncertainty, nothing going on. Just the fact that you connect them shows up this way. Okay, let us do one more thing. If I go back, and you can clearly see that as you keep going forward, the last vehicle has the overshoot is increasing. You also see that the settling time is also increasing. So there is some you can clearly see the effect in both the transient and the steady state response in this case. When I say steady state, I mean not steady state, but transient response. So you see that behavior. Okay. Now let's do something else. Instead of the traditional leader follower, let us close this by closing 4 with 1. So now I close this particular system, and I redo this simulation, and you can very clearly see that the follower agents no longer depict the desired model response. Each one of them is quite different now and then the transient as the group settling time has significantly increased compared to the previous one. So this is just to illustrate that how you connect them has a significant effect on how the group will perform, tracking this reference, which is given to be just that particular value here. This is for agent 0, which is the reference trajectory, right? So we make that case. Now, if you compare this setup to another setup. Now, what I did was, the only thing I did was introduce another edge here between 1 and 2, but then the reference input is given to both. This is closed, but then the reference input is given not only to 1, but to 2 as well. So if you do that, you find that the settling time is improving, and so on. So you can go ahead and now put 0 onto 3 and then give the input to 4 as well. And you will see that if everybody receives the command separately, then their responses converge, which means if this is the objective that you want, where every agent has to track this one, maybe you should not have any cooperation. If you can give this reference signal to everybody independently, you're fine. But that's not how a group or a team performs. You're looking at more of a negotiated activity. So the question that you want to ask is, are there going to be some topology, some other kind of topologies that will help you recover some of the earlier performance, or are there other things that this particular formation is more robust to? For example, say disturbance accommodation or something of that kind. So you would like to investigate something of that kind. Okay, so let's see where we are. So we are looking at robust stability margin for cooperative system. This is again just a recap of a very simple idea that we know from linear single input, single output systems. Essentially, we look at the magnitude phase plot of K times G of S and look at basically how the system performs. So now that we understand that being the case, where we know that the connection topology affects how much of the individual vehicle performance can the group recover. We understand that. But then, like I said, we have other issues to look at, which would be things like, okay, what about if there is a delay in the communication from agent 1 to agent 2, how does that affect the group performance? So let us look at that. Now, in this case, we are trying to look at link imperfections to study the robust stability margin. And we want to characterize this group stability margin, not just that stability margin, but we also want to look at the input delay margin in this case for a system setup like this. Again, I want to go back and say that the UI, each one is that F16 short period agent, and individually they all have a controller, and that particular controller has been derived using whatever LPV technique that I had said earlier. So that is persistent throughout. Now, this is just showing how I put together each of these particular vehicles. And now I have, on top of all of the whatever may be the individual controller, I do have now an additional term that I have to add, which is basically coupling these particular vehicles through a control protocol of this kind. It's a very straightforward protocol that is analyzed. So in this context, we use the same. Now, this would be for a delay-free agent. But then if you have an input delay, then the input delay manifests in this form. And if you're looking at whatever the plant transfer function might be, we want to derive certain criteria for consensus for all these vehicles put together. First, without the delay, and then we want to study the effect with the delay. Okay. So if you were to look at, say, the criteria for consensus for all these vehicles, we want to look at essentially the eigenvalues of this particular system. This is again building off from very very traditional Bode and Nyquist type of ideas going forward. So this is something that we know from systems in general. So if you have your eigenvalues here, then the instability essentially would mean that some eigenvalues are going to cross over to the right-hand side. And the way to set it up is to say, okay, if you have a single input, single output system, we studied this in elementary control theory or first course in control systems, where you have your system plant like this, and then you're multiplying it with some magnitude and a phase term here. And when you keep M fixed and then you only vary phi, then you see what happens to these poles. That gives you an idea of the phase margin. On the other hand, you only vary M and keep this keep this equal to 1 and only vary M to see how that moves. That gives you like the gain margin equivalent or so, the idea behind the gain margin and so on and so forth. But we want to utilize this idea and then generalize this to connected systems. And that is done this way. So we create some sort of an artificial perturbation term here that is applied to the cooperative system. This is the cooperative system GP, and delta is the perturbation that is applied in the feedback path. Then what we want to do is we want to find what is this destabilizing perturbation. We want to find the destabilizing perturbation, and from what the destabilizing perturbation is, we will then extract both the gain margin, the stability margin, and the delay margin for this particular situation. So think of it as follows. So now the delta that I have here, I can write the delta as basically do a polar decomposition and write delta in this form. Suppose I write delta in this form, where there is R, which is a symmetric matrix here, and then you have U, which is a unitary perturbation. And think of U expanded like this, with this property that the U transpose or the Hermitian times U is equal to identity. So if that is the case, this is like a generalization. This delta is equal to RU is a generalization of the traditional complex number. So R serves the same role as this magnitude, and U serves the same role as this phase. So if you go with that idea, then you can see very clearly that if R is set equal to I and delta P is unitary, I can then calculate the phase margin given that. Then from here, I can synthesize the delays because I will know the critical frequencies at which that happen. And for the gain margin calculation, I actually set the U, this U is equal to identity, and compute what should be the value of R that will give me the smallest possible R that will cause that system to become unstable, right? So it is now very clear what I should do is each of these things will then span into some sort of basically some optimization criteria. I'll get to that soon. Okay, so before we get that, let's suppose you have the singular values of your GP. So you look at the singular values of your GP, what you want to know is this value, peak singular value at 1. You can find out actually computationally, you can find out this particular band, which is called the omega region. We call that the omega region, where it is crossing this 1. There could be if there are multiple, then we keep track of all of them. But then what you do is you find out within this particular region, where is that peak that is happening, and that is of importance to us because that gives me the omega sub p, where that particular thing, that is the destabilizing perturbation that we are interested in. So these are all summarized in our paper, Robust Stability Margin of Continuous Time Systems here. This was published in the AIAA Journal of Guidance Control Dynamics in 2022. What I'm trying to get to is this process of isolating this omega region and then calculating the necessary quantities for you to determine the stability margins is essentially posed as 3 separate optimization problems. One of them is basically just find the infimum of this particular quantity here. Then from there, you can calculate once you find the fees, then you can calculate the delay margins, and then you can find the gain margins again through a simple manipulation like this. I don't want to go to the details here. They are all there in this particular paper to see. Okay, so let's get to the results. So we did that. Then, like I said, we applied to the same F-16 Vista basic airplane. We go ahead and put that together, and we assume that these aircraft are operating at, say, so there are 3 in this formation. And then I set up a particular formulation here where 1 talks to 2, 2 to 3 is bidirectional communication, 1 to 2 is unidirectional communication. So that gives me a particular topology. I set that up and then I calculate the margins. Now, in our proposed approach, we find that the margins span this particular range, that is the phase margin, and the gain margin sigmas are basically in this range. Now, we compare this with whatever margin calculations can be done through MATLAB's disk margin function. So MATLAB has an inbuilt, basically a disk margin function. If you use the disk margin function, this is the range that you get for the phase, and this is the range that you get for the gain margins. Now, what we did was we then constructed a perturbation matrix with a phase value of 0.8 radians and another phase value of 0.9 radians, and with singular values 1 and 5. Notice these numbers are all within 0.8 and sigma. These numbers are within the kind of range that is predicted by by these proposed terms here. Okay, if you look at these terms, these are outside of the ranges prescribed by the disk margin, which means if you were to calculate the disk-based margin, you would be tempted to think that these values are not possible because the system is unstable for these values. However, our proposed approach does have these numbers within its particular range, so we are less conservative in that sense with both these predictions. And we go ahead and simulate it, and we find out that with those values, we are actually stable. Consensus is achieved in the three vehicles. So this is an example that I just pulled out of our paper here. This just goes to show that the analysis that was presented and the results that we get there out of is relatively less conservative compared to what is out there. And we compared this only with the MATLAB disk margin toolbox, disk margin function. There could have been new results that we are unaware of, but yeah, that's the comparison that we had made. Now, we went ahead and tried this with higher order systems. This is a 4-state system. Again, this is an example from Professor Frank Lewis's paper. I think this was an Automatica paper in which they used the same example to demonstrate, to show some results. So here we have a connection topology of this kind where 0 again is a reference and the vehicles are connected this way. So we tested this. So for this particular example, we looked at the delay margin and and now in this case, because they were using an LQR type of a controller for there, so we use the same standard LQR controller for all the agents. Notice this is a simple spring mass damper type of a problem, 2 springs and 2 masses type of a problem. So there is no LPV control here. We just do the baseline controller using LQR with, say, Q and R as these values, and we connect them. So each agent is this LQR controlled agent. And we put that together and we compute the delay margin for that particular calculation to be 0.424 seconds. Now, the other thing that we did was we looked at is there a particular topology that gives you better answers? So notice, in this case, it was this topology, which gave us a number like 0.2457. So we went ahead and did a directed path. If you think about a directed path, if I give, this is just a consensus problem. So if I give a directed path, this is like a leader follower, right? 1 to 2, 2 goes to 3, 3 goes to 4. It's a standard leader follower structure. In the undirected path, well, the communication is bidirectional between any two agents. So 1 and 2, it is bidirectional, 2 and 3, and likewise. Then you go to a directed cycle, so you close this. It's the same as leader, just that there is no leader here. It is a closed cycle. And look at the delay margins that we have. We have 0.2537. This is the highest for the delay. So the directed path has a higher delay margin compared to a complete graph where everybody is connected to everybody else. It takes some time to try to digest this because you would think that something like a complete graph is a good thing to have because everybody is talking to everybody. I have a feeling that everybody talking to everybody creates more chaos and less robustness. But maybe it is robust to something else, not necessarily the kind of consensus variable that we are looking at. So the bottom line here is this sort of analysis is okay, but you cannot generalize this as a general performance for all graph structures. It is just that a particular consensus variable and a particular problem that you're trying to solve may have a completely different type of a distribution of results than what we have found. But at least for our problem, which is more of just a consensus with a reference signal provided to say 1 and then look at that, we find that it is the directed path is more delay robust compared to a complete graph or somebody else. Okay, so now that we had this sort of an interesting distribution of results for different graph structures, we try to see, is it possible now to inject a disturbance somewhere inside of these particular to any particular agent, and if that would destabilize, say, the formation or something of that kind. So is it possible to even do that? So so we are looking at, say, a malicious agent that can suppose sense an agent or more and pass a fabricated signal. And the idea was to only explore a security issue of something like this in a multi-agent system. We haven't done much in terms of mitigation, but we have uncovered a very interesting modality. And there is more work that we need to do in this particular area to say, okay, how can I prevent something like this from happening, or how do I even detect? So this is interesting because we now have a configuration of some multi-agent system. And then there is of course, with the perturbation like this. But imagine if this was the same configuration, but then now you had an intruder, and what this intruder is doing is listening to a set of these states. Somehow it has hacked into a network and can listen to certain states and then fake a disturbance signal. And what specific disturbance signal would that be, or what is the characteristic of that particular signal? So you could potentially fake a signal and add it to whatever the X tilde comes here, and what is the consequence of something like that. Now, there is a YouTube video here which shows a Jeep being hacked remotely. Uh, we are already at 11:48, so I probably don't have much time to show that. Let me come back to this one a little later, but I can share the slides, so you can always access that particular video. Look for a Jeep hacked video on YouTube. It's very popular. Okay, so when we do that, I look at a 3-agent system just to demonstrate this. I have a malicious node that is sitting outside and passing a fake signal. And notice here, and the signal that is being sent is a very specific signal of this kind, where this phi is 2.58 radians. This is slightly more than whatever is the phase margin of the system, essentially. So once you pass that, so there is a signal that can be passed this way. And notice that this is how it was generated. And when you do that, you see the agents just, the states just blow up. There is no consensus. So the formation is unstable in this case. So it's like a successful attack in that case. But then if you notice that same M, when it gives a signal to now this particular agent here at 1, nothing happens. There's no problem. Now it is important to know that that is the case, because this particular situation, agent 1, this is not a root node. So in this case, 3 is a root node. So if 3 is compromised, of course, 1 and 2 are also compromised because nothing comes back to 3 from either of those agents. On the other hand, here, 1 is not a root node. So even if there is something malicious that is sent here, it goes through the network and comes back to 1 for some mitigation action. So in this case, you see that in this case, even with a phi that is 3 radians, which is more than phi, the destabilizing phi that we had looked at previously, you still have an unsuccessful attack. So the takeaway here is find the root nodes in your network and protect the root nodes, or have monitors around the root nodes to see if there is any spurious input that is coming to the root node that is somewhere near your network destabilizing frequency. Because remember, the network destabilizing frequency can be calculated ahead of time, and the only thing it depends upon primarily is basically the way in which the agents are connected. So that has that bearing there. Okay, I think I have a few more minutes to get there. So we talked about one aspect of that research, which was all about trying to design robust stability margin calculations. And notice all the calculations that the metrics that we came up with, which is the group stability margin and the group delay margin and the group performance margins, all those are very quickly evaluated in using traditional functions. Once you have the code for that is all very straightforward. It doesn't involve a lot of tedious computations, and it can be quickly evaluated for the entire set of systems that we have. Of course, the overhead initially is that you still have to do this low-level control design, and that could be an LPV design or some other design that could take some time. Okay, but once that is established, for the group, the evaluation of these metrics are very quickly calculated. Okay, so let's get to finite time performance. I talked about this. Now we looked at a specific problem, and we were actually, this was what the funding solicitation stated, which was more about a threat neutralization type of a problem. So you have multiple agents trying to neutralize a threat, and there were certain properties. So we went through this. The question that we posed, or rather the problem that we posed that we would want to study is a finite time to go consensus problem. And in this case, what I mean is the following. So essentially, I have multiple agents trying to neutralize a threat. So from when I know that the threat is incoming, I am going to deploy some assets. And the problem we want to solve is how can I get all these assets to show up at the exact same time to neutralize the threat? Not in any particular sequence, but I want all assets to arrive at a particular time to neutralize that threat. Now, that is like a time to go from, so there could be multiple assets deployed from multiple stations. So the time to go to a particular location is different depending upon where they are, but they all want to get there at the same time, which means they'll have to modulate their speeds as they approach this particular target. Now, in a very common, so that would be like a salvo type of a defense problem. Now, to give you a common example, imagine there were 5 friends who all decided that they want to get to a particular Starbucks location. They know where to go to. They know the Starbucks location, but they want to get there precisely at, say, 5 p.m. They're all starting from different locations, but they want to get there precisely at 5 p.m. Now, the only variable they're allowed to exchange is they look at their GPS, look at their GPS screen, and the only thing they can report to each other is the time to go. So one can say 1 hour, the other can be 20 minutes, somebody else is 15 minutes away, but then there has to be consensus because you want to get there at the same time. So maybe you don't have a final 5-time restriction. So let us assume that I remove the 5 p.m. restriction and say, okay, you keep talking to each other and arrive at that location, but make sure all of you arrive at the exact same instant. So that is the problem that we pose here. So the threat location is known to all the agents. However, the only variable that they can exchange among themselves is the time to go. Now, the good thing about something like this is if somebody hacks into this particular network and can listen to, say, only time to go, you can't make sense out of what that number is. However, the agents know what this particular number means, right? So it gives you some level of security in that sense and minimal communication in that sense. So we are intercepting a target using distributed agents. They all exchange information securely at the same time. So the first thing you want to do is share a time to go. This is a very difficult quantity to calculate. So time to go is not really easy to calculate for a typical kinematic representation that is given here. But what we can use is an estimate of where you are. So assuming that you are on that particular path to this particular goal location, so you can compute some estimate. And this estimate is what is being shared. Now, once it is shared, they all decide that, okay, I have a set amount of time to go that is a consensus variable, and they all the agents now modulate their speeds so that they arrive in that particular time to go. But then it is not, so after some time, you reevaluate this consensus. So that the question becomes, then the question is, how many times would you have to reevaluate this consensus time to go until you actually meet the final objective? So that is this particular framework, that is this particular problem. So I'm not getting into the details of this particular derivations and all those things for that, but we do have a paper that summarizes all these things. Essentially, we have a finite time. We have a controller that gives you a fixed time to go convergence, and then we can do a finite time. So this is a very standard there are ways in which you can derive a finite time convergence control laws from the sliding mode type of literature. So we do this and we can intercept the target in finite time. This is basically summarized in this paper, leaderless time to go protocols for same time position consensus. This was published recently, and that's the link to the paper. So then there are other criteria because if you say that everybody exchanges their time to go, then what protocol do you follow? What is your so we use three different kinds of protocols. So one protocol says, okay, there are multiple vehicles, they all share the time to go. So let us agree that we are going to take the maximum out of these time to goes, and we will then design our speed modulations to get there in that maximum time to go, and then keep reevaluating that at a specified time horizon each time. Well, the maximum time to go would mean that many vehicles will have to slow down because they are now going to try to catch up with the slowest among the group of vehicles. Then there is the min time protocol, which would mean that all vehicles will take the minimum of the time to go that is shared among them and use that minimum value. Now, if that is the case, there will be some vehicles will have to speed up to or significantly accelerate to get there in that particular time to go. Now, what happens if there is a particular vehicle whose speed is limited, that I cannot accelerate beyond a particular speed, which would mean then that you have to have a compromise. And that is our achievable time protocol. So we actually work on all the three protocols, and that paper discusses all the three protocols to get there. So like I said, the max time protocol just requires us to find the max. It is the longest time to converge to the target, and the agents move slower. On the other hand, you have the minimum time protocol, which does the same thing, but it takes the minimum now, and it is the shortest time to converge to the target. And some agents move the agents have to move much faster compared to all other protocols. Now, this is not necessarily achieved if some agents are throttled. When I say when they are throttled, what I mean is when they have to limit their speeds. Suppose there is a saturation on the amount of the speed that they can travel, then you have an issue here, which is basically which will not permit convergence to happen. In that case, so this is just showing a simulation of basically a maximum time protocol situation where you have time to go estimates, vehicles start from different locations, and these are their velocity, the radial velocities along the line of sight. And you see that as the time to go convergence has already happened in very few iterations. The first 3 seconds or 4 seconds, we already know what the time to go is for the entire group, and the entire group then executes that particular protocol, and you achieve the convergence to the final state. So that's how all these vehicles arrive at the same location, but they all start from different locations. So then we also work through other problems, which is basically when you have a maneuvering target and you have to perform through. So I'm not going to go over all that. So let's just get to the achievable time protocol. So in this case, this is a slightly different. So what happens is these are 6 agents here. And in these 6 agents, what happens is every time there is an agent with a red, indicates that that particular agent cannot increase its speed beyond a particular value. In that case, there will be a subset of agents that will follow a switch to a maximum time protocol because they are now limited by that maximum speed. and the others will just follow whatever their speeds are that is allowable at that point. We see that in that situation, while that speed modulation has changed for some of them and not for some of them, you do see that final convergence does happen in this particular scenario. So we have successful results in this case too, where we can show that the terminal error is bounded and all those things. So all this is summarized in the paper in that case. Later on, we went ahead and implemented this on a distributed framework, setting up a network of this kind. I think, hopelessly out of time. So let me just summarize finally. So I presented basically an LPV framework for single vehicles. Then we have group stability margins and delay margins that were summarized for groups of vehicles. And we discussed some performance assessment guarantees using finite time criteria applied to basically interception of threats. Some of the papers that came out of this work over the last 3 years and a bunch of conference papers that came out. I want to thank my sponsor from ONR for this work. And of course, Doctors Dewan and Yucelen for inviting me to give this talk. These are the students who actually performed all the work. These three have all graduated. Shobit Voleti is still, he's finishing up. He's going to graduate in fall. But this is what their contributions were in each of these particular areas. Thank you. I don't know if we have time for questions. Thank you all for listening.
Thanks, Kamesh, for the presentation. Well,
Thanks, Kamesh.
It is 1 p.m., but we can have a couple of quick questions if you want.
Sure, I'm fine.
Okay, if you have time, let's see. Well, it's time to take questions from the audience. If you have questions to Kamesh, you can simply do it by unmuting yourself, or you can put your questions to the chat box.
I do have a 10-minute window. I'll leave it around 12:10, 12:15 or so.
Sure. It should work. Our audience usually shy, and you gave a lot of information. Probably it's gonna take some time to digest, but yeah, if you have questions, please go ahead.
Feel free to email me if you have, if you want to follow up on anything or you need anything pertaining to the talk. I'll be happy to share.
Kamesh, this is Radhakant here. So
Yes.
how does it generalize to heterogeneous agents basically? Let's say most of the presentation was homogeneous. Right?
So we have actually the time delay work and all that was also done for heterogeneous systems. I had a few more slides that extended it to heterogeneous. I didn't get a chance to get there. There were some backup slides. But I can share a couple of recent papers that we have, which actually extended this to heterogeneous systems too.
All right, thank you.
Because what happens is when you go back to the formulation, the low-level controllers, once they're all done, the only way the higher level controller is connected is through a coupling gain. Maybe I can pull up my slide to show you where that is. Yeah, so if you look at this particular slide here, whatever be the low level controller, that is fine. The only thing that we are interested in designing later on for the group of systems is through this coupling gain.
Will come for me or for everyone. Your slide is not visible to me.
We cannot see your slides. Yes.
Oh, okay. You cannot see the slide?
We just see your blank screen. So yeah, now it's okay.
Now it's okay?
Not
No, still same. We see your Windows screen.
Yeah, maybe like to answer and share it again. That will work.
Oh yeah, I'll do that. Can you see it now?
Yeah, you can see that.
Yeah, so here in this particular case, there is a coupling gain here. That coupling gain is the only gain that is different. So this C. Once you have the low level case, once you have the individual low level controllers, you can group all of that together. Only the coupling gain is the one that couples different agents. So you can have multiple different agents, each having K1, K2, K3, whatever they could be that way. So this is just shown for that case, but you could extend them with K1, K2, K3 along this particular leading diagonal that I show here for the controller. The coupling gain is the one that connects all of them.
All right, so only that one will change, the gain will change.
Yeah, yeah.
And how exactly you deal with the time delay part of it? And you told about it, what's the philosophy? Yeah, 14.
Yeah, so the time delay part of it, it is basically we convert this into some sort of it's a different problem. So when we get here, I have not included the time delay results here, but that's a completely different paper I took out. So this is just calculating the delay margin from here. That is a completely different body of work. So this doesn't explicitly talk about time delays in the or other non-commensurate different time delays in the links and all. This only talks about input delay that you can have here, and that is why I talk about the delay margin. And that is how the delays are addressed here. In simulation, you can introduce different delays to show how it works, but you have to make sure that, but you are able to guarantee performance so long as your, where is that? Yeah, this was so long as your delays are smaller than this delay margin value, you will be fine.
All right, got it. Thank you.
Yeah, yeah.
Interesting talk. See.
Yeah.
Thanks a lot, Kamesh. I don't want to take your time since you have other duties, but like if they have questions, they can email you, right?
Absolutely.
Mm-hmm. And this video will be posted. As you know, we can send you the link when it is on if you want to share with your students, colleagues. Well, thank you again one more time and hope to see you in person soon.
Yeah, thank you very much. Sure.
Have a great day, everyone.
Yeah, bye all.
Thanks all, bye. Thanks, Kamesh. Thanks, Merve.
Thanks, Tansel.